My name is Przepióra. I'm a senior software engineer at Atlassian. So you can add this to the list of things you can hate for me for, because what I'm doing daily, I'm working on Jira Cloud. So who doesn't use Jira Cloud here? I thought so. Okay. So as I said before, my daily job is developing Jira Cloud. I'm a molecular biologist by my education, but I've never worked in a lab, actually. I just decided to switch my careers and became a software developer. And by hobby, I'm a home brewer. This QR code, this QR code here is my LinkedIn. So if you want to get in touch with me, just use the QR code. I will show it at the end of the presentation as well. So yeah, without further ado, what are we going to talk about today? So I want to talk about Java memory model, because, well, that's the title of the presentation, right? But before we actually talk about the Java memory model, which is a teeny part of this presentation, we need to talk about all the things that are before the JMM, about the modern computers, how they work, why do we need Java memory model, and why we actually can use the Java memory model to our advantage as software developers. Okay, so we'll talk about how modern computers work, why do we have something like cache coherence, and why is it important for us as software developers. We will talk a bit about the metal, about the CPUs and their caches and the messy protocol. We'll get to that. We'll talk about a volatile keyword in Java. Who uses volatile in their Java code? A couple of people. Okay. So you will know why it's not enough. And then we'll get into the Java memory model itself. I'm going to describe it in simple terms. And then I will also share some materials that you can use to learn more about the model itself and how to actually properly develop multi-threaded concurrent applications in Java. Okay, so how do modern computers work and why does it matter? The thing is, so the problem is that in current modern computers, the program is not actually executed in the way you wrote it. So if you have a set of instructions in a single-threaded computer program, it doesn't mean that the CPU will execute those actions in the order that you specified in your program. For example, we have a set of instructions. We have 4 variables, 4 memory places, and we assign 3 to A, 5 to B, C to A, 8 to C, and then we have another operation at the end. D is A plus B, right? So you would expect that D is how much? 8, right? And that's how computers should work, right? That's what we expect from them. But the thing is that with modern CPUs, the actual order of execution on the CPU might not necessarily be 1, 2, 3, 4. You can have a different order because CPU decided that it's going to be faster, for example, but the end result will still be the same. So when this block of code is executed, we will always have at the end A equal 3, B equal 5, C equal 8, and D equal 8 as well. But we can have the third instruction executed first by the CPU. We can have second instruction executed second and the first as a third. So that's a list of possible orders. Why this reordering happens? What are the sources of reordering given that we write a Java program? So the first thing that then can reorder your Java program is the Java compiler, the Java-C executable. It can actually emit bytecodes that are a bit different to what you've wrote in your program. So that's one source of reordering. The other source of reordering might be the just-in-time compiler in the hotspot virtual machine, right? So it can take the existing bytecode, even if this existing bytecode is the same, has the same order as Java program, the just-in-time compiler might optimize it and figure out, okay, so we need to change the order a bit so that it actually executes faster. And then CPUs can do this as well. So a CPU can take a set of instructions and look at it and, okay, I think if I'm going to switch the order a bit here, I'm going to work with it faster, right? And then the other thing, even if the CPU doesn't change the actual order, we need visibility of those operations. That's what counts. Even if the CPU executes the operations in the same in the same exact order that you specified in your program, the thing is, it doesn't matter because it needs to put it into the main memory for you to be able to actually see the actions performed, right? And CPUs write to memory through caches. And CPU might come to a conclusion that, okay, so even though I executed those operations in this order, when I'm putting this back to main memory, it's going to be faster if I change the order of writing to the memory. So that's why we have the reordering. That's what are the sources of instruction reordering in your Java program. Okay, so you might wonder, okay, that's scary stuff. My program is not executing the way I wrote it. So that's why Java Virtual Machine gives you some guarantees about how the results of executing your code will look. So the JVM in a single-threaded environment basically hides those tricks from you and from the environment, hides those tricks applied on your program by the environment and have no other effect just than speeding up the execution. The Java language specification requires the Java Virtual Machine to maintain this within thread as if serial semantics. So basically, excuse me, this means as long as the program has the same results as if it were executed in the order that we wrote it, in a strictly sequential environment, all those changes that are performed by just-in-time compiler, by CPU, by cache, are allowed, but the effects need to be the same. So basically, Java Virtual Machine says, even though CPU makes those changes in the execution order, even though caches are written in a different order, if you write your program, single-threaded program, A equals 3, B equals 5, C equals 8, D equals A plus B, in a single thread, you will see the exact results that you're expecting. That's what Java Virtual Machine guarantees to you. Nice, right? Okay, so let's jump into IntelliJ for a while. So this is a simple program written in Java. I'm actually using Java 21. And the thing is, we have 4 variables. Those are static variables, A, B, X, Y. And then we're going to comment it for a while. We don't need that just now. So basically, we have 2 threads that are working on A, B, X, and Y. They are all set to 0 in the beginning because, well, that's static initializer, so we are guaranteed that when the code runs, it's actually equal to 0. And then, in the first thread, we want A to be equal to 1, and we want X to take the value of B, right? And the second one is B equals 1, and Y takes the value of A, right? We start those 2, we wait for them to finish, and then we print the results, basically, all the, what are the values of all the variables. I'm using Java 21 preview feature, which is string templates. Basically, it's easier to write it that way, to format this kind of output. Okay, so what do you expect this will actually print? Yes, it depends on the thread scheduler, actually, right? So we can have one execution where the first thread is starting and then it finishes, and only then the second one starts and then finishes. And then it's probably the most common result I've seen from like trying to run it a couple of times, but then we have A equals 1, X equals 0, right? B equals 1, Y equals A, and A is already set to 1. Right? So let's run it and see. Yeah, it's going to take a while. A1, B1, X0, Y1. That's what I said before, right? But that's not the only possible result, because we can have, well, I'm going to simulate it a bit here, because I'm going to just add a sleep here. so that we can have the other thread step in. So this makes it a bit more probable that the B thread will actually start executing after the first instruction, right? So if we do that, we can see that you can assume that there is no thread sleep, right? It's just for presentation purposes. Okay, we need to wait 10 seconds. Sorry about that. But I can take a sip. Right now, what we see, what is happening, that this line executed first, then we have this line executed because we were sleeping here, but let's assume we don't sleep. It's just thread scheduler that decides to, okay, so we need to switch threads. And then we have x equals b. Well, b is already set to 1, so we have x equal 1 and y equals 1. So yeah, that's pretty much it. Let's get back to presentation. There's one more thing that can happen, is that within the thread that we had, within the both of those threads, we can have this reordering that I mentioned before as well. So we can actually have this line executed first and this one executed as a second, because it is in one thread, and those instructions are independent, right? So one is about writing 1 to A, and the other one is about X. They're not intertwined, right? So there is no connection between them. So what can actually happen with reordering is that we first set X to B, and then we set 1 to A. This is perfectly possible in modern computers. And Java Virtual Machine will allow that, because this is a single thread. Java Virtual Machine has no way of knowing that you're interacting with those variables from another thread, right? At least not with that simple code. Okay. So moving on. Possible outcomes. Well, that's one way of the code could execute. So we have A equals 1, then the second thread steps in, then we get back to thread 1, and then we get back to thread 2. Or we can have thread 2 execute first before the thread 1. That's perfectly possible. And then we can have the reordering happen in the second thread as well. Right? Like this. Okay. And then there is another problem. This is actually perfectly possible. This result is perfectly possible on a single core computer as well, right? Because we don't have, we have threads, but we can execute multiple threads on a single CPU. It's going to be slow, yes, but it's possible. And this can also happen on a single core CPU. Okay, but the problem is that with modern computers, more and more of them are actually using SMP, symmetric multiprocessing, which means that there are multiple processors using the same area in memory, and you get a visibility problem out of it, because you can have the CPU read data from main memory and have this data stale in the registers, right? Because some other CPU already changed it in the memory. So that's why we need some way of assuring that there is coherency. We're going to talk about it in a moment. But let's talk about one thing. Of course, we could force computers to do what is called sequential consistency. So we would ensure that every processor knows what every other processor is doing at all times. But that's very expensive. Synchronization between CPUs would be very expensive, and most of the time we would actually not need this information. So that's why processors relax their memory coherence guarantees, so that we can have improved performance. And the thing is that the so-called architecture, which is CPU and memory and the operating system, have something that is called memory model. And this memory model tells programs what guarantees you can expect from the memory system, given the when we're talking about visibility of the changes. And the platform memory model specifies something that is kind of instructions for CPU that are called memory barriers or fences. And those instructions give the additional coordination guarantees required when sharing data. So basically it means that when there is a memory barrier, it means to the CPU, okay, so now make sure that all the changes that you've made are visible to other CPUs. Simplifying a bit, but just a bit. And now you might think, okay, but I'm a Java developer. I actually don't care about what is the metal I'm gonna run my program on, right? Write once, run everywhere. It's gonna be probably Intel anyway, right? Actually, not really. I mean, AWS introduces their, what is it called? Yeah, Graviton instances, which are not using Intel, right? And you as a Java developer, frankly, should you care? Or maybe you are a software developer using modern MacBooks with M2. Those are not Intels, right? And you want to develop your Java software and don't care where it's going to run. Is it going to run on Graviton or on Intel or AMD? It shouldn't matter. So that's why Java had to come up with its own memory model. And the thing that makes Java memory model different from other memory models, from platform memory models, is that it doesn't expect the software developer to insert those barriers into their code. It actually does it automatically for you. That's the nice thing about Java Virtual Machine. It deals with the differences between the Java memory model and the underlying platform memory model, and it inserts those memory barriers at appropriate places. So, one convenient mental model for program execution is to imagine that there is a single order in which all the instructions in the program happen, right? Even if we split the program into different threads and we don't care about the processors they execute, and each read of a variable will see the last write of the in the execution order to that variable by any processor, right? This is happy but very unrealistic model, and we call it basically the sequential consistency. So what I've seen is that many software developers mistakenly assume sequential consistency, but it actually it doesn't happen on any modern multiprocessor system or even on the Java virtual machine. So I would say that the classic sequential computing model is just a vague approximation of what actually happens on multiprocessor systems. The thing is that modern shared memory multiprocessors and also compilers for those systems can do some surprising things when data is shared across threads, unless you've told them not to do that through the use of memory barriers, right? And again, the fortunate thing for us Java developers is that we don't need to insert those barriers, because if we follow the rules of the Java memory model, Java virtual machine will do that for us. Okay, basically by proper using the synchronization keyword or other elements of Java language. Okay, the thing is, JVM inserts memory barriers automatically, and we need not to care about that. I was talking about cache coherency a bit. So why is it important? As you can see, this is a vague approximation of how modern computer looks like. So we have CPU, we have a couple level of caches, and then we have a level 3 cache that is shared between the CPUs, and all the writes to memory go through those caches. And the thing is, CPU, caches, and memory are all connected via bus, and we can actually use it to our convenience, because caches can be made coherent. When you make a change, when you write back to memory, you can actually have the copy of those changes passed to other caches on the same level as well. And you can even have it done atomically. So you can actually make change in one place and have it reflected in other caches as well. So the thing is, caches aren't just dumb memory storage units. They actually have very advanced protocols for asserting this kind of coherence. And One of the protocols, the earliest protocols for that was called Messy protocol. And it has different variants, but I'm going to talk about Messy briefly here. So each cache line has one of the states, of those 4 states, modified. The cache line is present only in the current cache, and it's dirty. Basically, it has been modified from the value in main memory. And the cache needs to write the data back to the main memory at some time in the future, before permitting the read of the no longer valid main memory state. Okay, we have exclusive state for a cache line. This data has been modified and is in sync with the data in main memory, and no other sibling cache has this data shared. This data has not been modified since it's been read from the main memory and is in sync with the data elsewhere. And some other sibling caches can have also this same data. And invalid, basically, this data stale and should never be used. And by using the combination of those 4 states for CPU cache lines, we can actually achieve this cache coherency by basically marking cache lines with those 4 states and transitioning between the states. So I'm not going to go into details right now because that would make it a whole different presentation, and I don't think you're that much interested in that. So I'm just going to stop here. If you want to read about it more, I can provide you with materials later. Okay, now let's talk about the volatile keyword. What is a volatile variable?
I know that it prevents some reorderings. It is like there was no cache unless we do some kind of not like if we set a value for depending on the previous value, then it won't work. But for just setting a new value, it's okay.
So basically, volatile. And why would we need a volatile? Because we have coherent caches.
It is about synchronizing.
Yeah, that's the side effect. But why do we need volatile if caches are coherent? So we can just push something out of the CPU and have the cache coherency protocol deal with it.
So if we mark a field in an object volatile, it means that if we modify this field, other threads will observe the change without using a synchronized block. That's at the language level.
Yeah, so basically what volatile is that it guarantees atomicity for a single field, for either reading from it or writing from it. But the thing with a volatile is that if you want to perform a thread-safe operations like compare and swap, right? Basically, read followed by a write, understood as one single operation that is atomic, that cannot be split into 2. Volatile alone will not allow for doing that. And there's no way of implementing it with volatile. Volatile guarantees atomicity to only a single operation that is either reading or write. So yes, you can piggyback on it. So basically, if it's atomic and it actually inserts a memory barrier for you, you can have all the things that happened before writing to a volatile be made visible to other threads. That's true. But the thing is, my point here is that cache coherency is not enough, because you can read something, have it changed, and when you write it back, you won't see it. The change that was made before you write it won't be seen. So basically, you will shadow a change that was done, for example, by a different processor. So the thing is, data that is read into CPU registers is not kept in sync with data in cache or memory. And again, compilers can make all sorts of optimizations when it comes to loading data into registers, writing back to the cache, and even reordering the instructions, as I said before. So all those shenanigans with the code are done with an assumption that the code will be run single-threaded. And there's basically no good way of making sure that the compiler takes your multi-threaded code and see, okay, so this reordering can be done and this cannot be done. So that's why data that is at a risk of race condition needs to be manually protected through concurrency algorithms and through language constructs like atomics and volatiles and synchronized code blocks. Okay, so there's one more misconception that I've seen was quite common, at least some time ago, about volatile. So volatile was meant that it forces writing to the main memory, but that's not true. It just forces visibility of writes to other threads as soon as a variable has changed, right? And it might mean on a modern CPU that the change is only passed on to caches, right? It's actually not going to the main memory. Okay, so as I said before, volatile is not enough for proper multi-threaded computing. So enter the Java memory model. That's what we're going to talk about right now. What is Java memory model? This model of how the memory works is specified in terms of actions. Terms of actions that include reads and writes to variables, locking and unlocking a monitor, and starting and joining a thread. The Java memory model defines something that is called partial ordering. Anyone who studied mathematics here? Okay, we're going to talk about partial ordering on the next slide. So this partial ordering is called happens before a relation in the Java virtual machine specification, and it defines an order on all actions within the program. It tells what reorderings are not possible, basically. So what is partial ordering? So you can think of it like, for everyday example, we can prefer rock music to pop music, and we can prefer burgers to pizza. Who prefers pop music to burgers? That's the idea of the partial order. So it gives you a way of ordering some things in the set, but not all of the things in the set, right? So you can tell this comes first, this comes after this, and this comes after this, but it doesn't necessarily tell you that this comes after this, right? Okay. So there are actually a couple of rules that the Java memory model defines for this partial ordering. So the first thing is, the first rule is that in a single thread, everything happens before every action that comes later in the program order. Right? So basically, we're coming back to this example at the beginning. Right? So this rule says in a single thread, this is a rule for a single thread. Well, there can be some changes in the order, in the actual order of execution. But you won't see them because when this block of code executes, you will see that E equals 3, B equals 5, C equals 8, and D equals 8 as well. Right? And that's what this rule says, the program order rule. Each ordered action in a thread happens before every other action in that thread that comes later in the program order. As I said, this is a partial order, so actually assignments to regular variables are not ordered. That's why we can have the reordering happen. Then we have a monitor lock rule, and that rule says that in a single thread, when we have a lock on a monitor and then an unlock in the program order, the unlock will happen after the locking. So that's obvious. That's how it should work, right? So we're expecting that we're not going to unlock a monitor before it is locked, right? But we need this for this model to be complete, right? That's a very, very easy to understand rule. Okay, the other one, a volatile. A write to a volatile field happens before every subsequent read of the same field in the program order. So if we, getting back to this example in the beginning, let's go to slide 6. If we make marked A as volatile, then the first action would always happen as the first one. And Java Virtual Machine would guarantee that, yes, A is always the first line is always executed first, and there's no way of reordering it or mixing it, swapping it with 3, for example. It's going to happen first because it's volatile. So that's the thing about volatiles. And one thing to note is if you're using atomic integer or atomic long, it has the same semantics. So if you write to an atomic integer or atomic long, it's basically the same as volatile integer or volatile long, only for the purposes of writing to it. Because atomic integers and longs have some other nice things that are also atomic. Like increment atomically or stuff like that. But let's not get to that. We'll talk a bit about that as well. The other thing, a thread start actually happens before every action in a started thread. Make sense? So before you run a thread, it has to be started, basically. That's what it says. And it has to be visible as started to other threads as well. So you cannot have some things happen in the thread without the thread being started already and being it visible to other threads. Okay, and then again, very simple rule, when a thread ends, everything that happened before the thread ends needs to be visible to other threads. So basically it says, if some thread sees another thread already finished, it will also see everything that happened in that thread. Okay, the same thing with the interruption. When a thread is interrupted, everything that happened before interrupting the thread needs to be visible to other threads as well. I think this is something that was missing from the original Java memory model, or was not so clear. That's why the Java memory model was updated for Java 5. And then finalizer. Who has heard about finalizers? Oh my, yes. Long time ago, there was this thing in Java that you could have some code executed when object was cleaned from the memory. Basically, it was not longer reachable, and the garbage collector could invoke a special method on this object for you. And the funny thing is that you could resurrect this object, for example, and then it would stick in the memory forever. Yeah. I have seen no code using finalizers for like 15 years or so, because this is a very, very ugly and bad feature of Java code that everyone should forget about. But still, the Java memory model needs it, needs a rule for it, because it means that before object is before object can have the finalizer executed on it, its constructor needs to finish. So it means basically the object needs to be really fully constructed before it's garbage collected and finalized. The actual rule says the end of a constructor for an object happens before the start of the finalizer for that object. And then some additional rules for the rules that we already mentioned. Transitivity. Basically, if A happens before B and B happens before C, it means that A happens before C, right? Makes sense. And then the total order is defined only for some operations that are possible in Java language. So even though actions like assignments, invoking methods, basically changing stuff in the memory, even though those actions are only partially ordered, synchronization actions like lock acquisitions and releases, reads and writes of volatile variables, those are totally ordered. So you can actually plot a line and a timeline and say, this happened here, like this lock was locked here, then it was unlocked, and then it was locked in a different thread, but only after it was unlocked in the previous thread. And we can have a total order for this kind of operations defined. So this makes it sensible to describe happens before in terms of subsequent lock acquisitions and reads and writes of volatile variables, right? An example. So we have two threads. We have monitor M that we lock on in one thread. So we assign 1 to Y. We lock the M. We assign X to 1 to X. And then we unlock M. And then some other thread steps in and wants to lock the M. So if it would want to lock before, like somewhere here in the timeline, it would have to wait, right? So it waits until this one unlocks, and then steps in and locks here. So everything that happened up to this point, right, all this stuff is visible to this thread, right? Because, well, we have the program order rule. Everything happened up to this point needs to be visible. And then we have the rule that, well, if I lock this one, I need to have everything that happened before visible, right? So we have this order specified. Okay. So all actions within thread A are ordered by the program order rule, and so are the actions in the thread B. Because A releases lock M and B subsequently acquires it, all the actions in A are visible to B. Okay. One thing to note. If we have threads that are locking different locks, then this won't happen, right? We have to have the same lock. Because there is no happens before relation between the actions in the different threads. Okay. A couple of side notes here as well. You can rely on the Java development kit, on the standard API of the Java virtual machine, to have these happens before actions performed for you as well, or insert in this order, having this order, because, for example, if you place an item in a thread safe collection, this is going to happen before another thread retrieves that item from the collection, right? So basically, it uses those basic primitives of Java virtual machine to make those guarantees to you as well. So it's building on a higher level from those primitives. If you submit a runnable or a callable to an executor, you have the guarantee that it happens before the task actually begins execution. And there's no magic there. It's just using those primitives from the Java memory model that I described to you. But it just makes it easier for you to develop concurrent programming without using those JMM primitives, and instead giving you a higher level API. That's what JDK Java util concurrent from Java 8 is actually doing. So you actually don't need to know all that stuff. You just need to read the docs for the classes that you're using from this package. Okay, some additional reading. I would recommend those two, Java Virtual Machine Specification and Java Language Specification. Come on, I'm joking. No, not really. I mean, if you want to, that's a very good reading, but it's very hard, and you know, there is a better investment of your time. That's a like 15 years old book that is still relevant for Java. That's Java Concurrency in Practice by Brian Goetz. This is my go-to book about Java multi-threading. Even though the APIs have grown, there are new APIs, this is still the Bible of multi-threading on Java. And why is it so? Even though this book is so old. Java memory model, the current Java memory model was introduced in Java 5, and the specification hasn't changed. The implementation has changed a bit because there were bugs, so they had to be fixed. But still, the specification hasn't changed. And the thing about JMM is that it is the first formally defined memory model for a language, for a programming language, that has a mathematical proof of being correct. So this is proven to be right by mathematics. Okay, and if you are interested in Messy protocol, then I would recommend reading a Wikipedia article about it. One side note, as you remember, I'm working for Atlassian, so we're hiring in Poland for remote positions. So if you want to look into what is available, the QR code on the left is the one to go to, and my LinkedIn is again here. Thank you very much. If you have any questions, I would gladly answer them now. Okay.